9.1 Linear Momentum. The outline of this video is as follows. We will begin by showing how the idea of momentum can be derived directly from Newton's third law by analyzing the forces between two interacting particles. With that motivation, we will then establish a formal definition for the quantity called linear momentum. Next, we will take some time to carefully compare linear momentum with kinetic energy. While they both relate to motion, they are fundamentally different concepts, and understanding this difference is crucial. To conclude, we will re-examine Newton's second law, expressing it not as F equals m times a, but in terms of momentum. This form of the law is more general and provides a powerful new perspective for analyzing motion. Let us consider a classic physics problem that demonstrates the limitations of the models we have studied so far. Imagine an archer with a mass of 60 kilograms, standing at rest on a frictionless sheet of ice. The archer fires a 0.030 kilogram arrow horizontally at a speed of 85 meters per second. Our goal is to find the velocity of the archer as they slide backward after the shot. We can try to solve this using our existing tools, but we will run into trouble. We cannot use the equations for constant acceleration because we have no information about the archer's acceleration. Applying Newton's second law is also difficult, as we do not know the magnitude or duration of the complex force exerted by the bowstring. Finally, conservation of energy is not a practical approach because we do not know the elastic potential energy that was stored in the drawn bow. This problem highlights the need for a new physical quantity to analyze interactions, especially brief ones like collisions or explosions. That new quantity is called linear momentum. Let us begin our derivation of momentum conservation, which starts directly from Newton's laws of motion. Our first step is to consider a simple, idealized scenario called an isolated system. Imagine a system consisting of just two particles. We call this system isolated because we assume there are no external forces acting on it from the outside. The only forces involved are the internal forces that the two particles exert on each other. For example, particle 2 exerts a force on particle 1, which we can label as the vector F sub 12. According to Newton's third law, forces always come in action-reaction pairs. This means that particle 1 must simultaneously exert a force on particle 2, which we call F sub 21. The third law tells us that these two forces are equal in magnitude and exactly opposite in direction. We write this mathematically as the vector F sub 12 equals the negative of the vector F sub 21. The key implication here is that if we add these two internal forces together to find the net force on the entire system, their sum is 0. This simple fact is the foundation for the entire principle of momentum conservation. Let us continue our derivation by using Newton's second law to replace the forces with their definitions. This substitution reveals a deep connection between force and a new conserved quantity. First, we replace each force F in our force sum equation with mass times acceleration, m times a. This gives us the expression m1 times a 1 plus m2 times a 2 equals 0. Next, since acceleration is simply the time derivative of velocity, we can rewrite the equation in terms of velocities. Assuming the masses of the particles are constant, we can bring the mass term inside the derivative. This allows us to combine the two terms into a single statement. The time derivative of the entire quantity, m1 times v1 plus m2 times v2, is equal to 0. The final equation tells us something profound. If the rate of change of a quantity is 0, then that quantity itself must be constant over time. Let us formally define the concept of linear momentum, a powerful tool for understanding how objects interact, especially during collisions. Linear momentum, which we denote with the symbol p, is defined as the product of an object's mass and its velocity. As the equation shows, p equals m times v. A crucial point is that because velocity is a vector, momentum is also a vector. It has both a magnitude and a direction, and its direction is always the same as the object's velocity. This means we can describe momentum using its x, y, and z components. The standard SI units for momentum are kilogram meters per second. For example, a heavy bowling ball moving at the same speed as a light tennis ball has a much greater quantity of motion, which is what Newton originally called this concept. This vector nature is what distinguishes momentum from the scalar quantity of kinetic energy. The key takeaway is that linear momentum combines an object's mass and velocity into a single vector quantity. You might be wondering why we need a new concept like momentum when we already have kinetic energy, since both involve an object's mass and velocity. This slide highlights why they are fundamentally different concepts, giving us two independent tools for analyzing motion. First, kinetic energy is a scalar quantity, meaning it has only magnitude and no direction. A key feature of energy is that it can be transformed from one type to another, for instance from kinetic to potential or internal energy. In contrast, linear momentum is a vector, so its direction is critically important. Imagine two particles of equal mass moving toward each other at the same speed. This system has a large amount of kinetic energy because both objects are moving. However, because their velocities point in opposite directions, their individual momenta cancel each other out, resulting in a total momentum of 0 for the system. Furthermore, momentum does not transform into other types of quantities. These distinctions make momentum and energy two separate and powerful principles for solving problems. We can now restate Newton's second law using the language of momentum, which provides a more fundamental and powerful version of this crucial principle. The derivation starts with the familiar form. The net force F equals mass m times acceleration a. We then substitute the definition of acceleration, which is the time derivative of velocity, dv by dt. For an object with constant mass, we can bring the mass m inside the derivative operation. This gives us the net force as the time derivative of the quantity m times v. Because we have defined linear momentum, p, as m times v, we can make a final substitution. This leads to the important result that the net force is equal to d, p by dt. This equation is actually more general than F equals m times a, as it correctly describes systems with changing mass, like a rocket burning fuel. The key idea is that a net force is what causes an object's linear momentum to change over time. This question tests our understanding of the relationship between kinetic energy and momentum. The key insight is that this relationship also depends on the mass of the object, which prevents a direct comparison without more information. We can express an object's kinetic energy, K, using its momentum, P, and its mass, m. The equation is K equals P squared divided by the quantity 2 times m. If we rearrange this equation to solve for momentum, we find that P equals the square root of the quantity 2 times m times k. The problem states that the kinetic energies of the two objects are equal. Looking at our rearranged formula, we can see that if k is constant, then momentum is directly proportional to the square root of the mass. For example, if a heavy bowling ball and a light tennis ball have the same kinetic energy, the bowling ball must have a much larger momentum because its mass is greater. Since we are not given any information about the object's masses, we cannot determine how their momenta compare. This quiz asks us to think practically about the difference between momentum and kinetic energy. The difficulty in catching a ball is determined by the momentum your hands have to absorb to bring it to a stop. Our task is to rank the 3 scenarios from the smallest momentum to the largest. First, let us consider case A, same speed. Since momentum equals mass times velocity, and the medicine ball is 10 times more massive, its momentum will be 10 times that of the baseball. Next is case B, same momentum. This is our baseline, the momentum of the medicine ball is exactly the same as the baseball's. Finally, we have case C, same kinetic energy. We can express momentum as the square root of the quantity, 2 times mass times kinetic energy. If the kinetic energy is the same for both balls, then momentum is proportional to the square root of the mass. This means the medicine ball's momentum will be the square root of 10, or about 3.16, times the baseball's momentum. Comparing these values, the order of momentum from least to greatest is B, C, and A. Therefore, the ranking from easiest to hardest to catch is B, then C, and finally, A. Let us summarize the core concepts of linear momentum. We began by defining momentum, symbolized by the letter P, as the product of an object's mass and its velocity. Crucially, momentum is a vector quantity, meaning it has both a magnitude and a direction. This definition allows us to express Newton's second law in a more general and powerful way. The net force acting on a system is equal to the time rate of change of its momentum. This relationship leads directly to one of the most fundamental principles in physics, the conservation of momentum. If the net external force on a system is zero, meaning the system is isolated, then its total momentum cannot change. This powerful conservation law, which stems from Newton's third law, allows us to analyze complex interactions, like collisions, without knowing the details of the forces involved. In essence, momentum conservation provides an essential and independent problem-solving tool in mechanics. To wrap up, let us consider a couple of questions that will help you apply the concepts of momentum and its relationship to kinetic energies. The first question involves an astronaut at rest in space who throws a hammer. Consider the astronaut and the hammer to be a single, isolated system. What is the total momentum of this system before the throw? Using the principle of conservation of momentum, you can determine what must be true about the total momentum after the throw, which will allow you to describe the astronaut's subsequent motions. The second question asks you to compare the momentum of a very heavy car and a very light bird that have the same kinetic energy. Start with the definitions for both quantities. Since their kinetic energies are equal, think about how the velocity of the car must compare to the velocity of the bird. Use this relationship to determine which object has the greater magnitude of momentum. I encourage you to pause and work through the reasoning for both questions before moving on.